go, let's go.
Am I allowed to take this one? No.
Oh, good morning, everybody. Welcome to the CGD seminar. This is also part of the Ocean Model Working Group Winter Meeting. And I would like you to introduce you to Margarita Markina. Rita has a PhD from the Shirshov Institute of Oceanography in Moscow and a postdoc from Oxford University. And she's been an NCAR since September 2024. And I'll let you tell you what you've been doing at NCAR and then introduce your talk.
Thank you so much, Gustavo. So yeah, I started in NCAR in September last year, and I'm working here on two projects. One is related to creating the forcing datasets for ocean models that is based on Error 5 reanalysis that we will be correcting from biases. And another project that I'm working on here is related to indirect ways of estimating AMOC, Atlantic Meridional Overturning Circulation. Yeah, happy to be here. And today I'm going to present on some of my previous work that I have done with Helen Johnson and David Marshall. And I'll speak on the impact of freshwater in the East Greenland Current on overturning in the Subpolar North Atlantic. So I wanted to start with some motivation and give you some introduction about the freshwater and changes of freshwater in the current and future climate. So we know that the decline of the sea ice in the Arctic is one of the most well-documented indicators of climate change. So we do observe the decline in Arctic sea ice over the past few decades. And we continue, and we expect to, in the future, we expect to see the ice-free Arctic. So this is, sorry. Yeah, I'll just use this one. It's easier. So this is the plot from the paper by Jan et al. In 2024, based on a number of CMIP6 models. And basically what they are showing is that by the end of this century, it is almost certain that we will observe some period of the ice-free state in the Arctic, at least in the summer. So another thing, so yeah, when we have the melting of sea ice in the Arctic, there is a large freshwater release. And a lot of this freshwater is being stored in the Beaufort Gyre in the Western Arctic. And here I'm showing some plots, also from the recent paper, that is showing that so the Beaufort Gyre is the wind-driven gyre in the Western Arctic, and it is, it does store all of this fresh water, and this is one of the reasons why, even though we see a huge decline in the sea ice, we don't really see a lot of changes in the freshwater transport into the Subpolar North Atlantic in the past couple of decades. And this is probably because this freshwater is being stored in the Beaufort Gyre. However, there is a recent paper that is showing that the Beaufort Gyre has stabilized in the recent decades, which implies that there is a raising potential for the large freshwater release in the future. And all of this freshwater, there are several different pathways of where it can go. One of them is through Davis Straits, through Canadian Arctic into the Subpolar North Atlantic, and another one through Fram Strait, so through East Greenland Current, essentially. So apart from this freshwater in the Arctic that we might expect to see in the Subpolar North Atlantic in the very near future, we also have Greenland. And here I'm also showing the plot from one of the recent papers that is basically showing that almost all glaciers in Greenland has lost their mass since 1985. So this also means the potential impact or the potential release of quite large amounts of fresh water into the Subpolar North Atlantic that may have some implications for the ocean circulation there. Okay, so this is one line of motivation and reasoning. Another line of reasoning is that because it's an ocean modeling meeting. So there is an evidence in the literature that some high-resolution models tend to have a salinity bias in the subpolar regions. And one of the hypotheses is that probably this is due to the larger transport of more saline subtropical waters into the subpolar North Atlantic. And this more salt in the subpolar North Atlantic leads to biases in the density structure in the subpolar region, which may lead to the overestimation of overturning in the subpolar North Atlantic. And here I just wanted to show you the plot with the position of the OSNAP observational array. So this is basically the only in situ observations that we have in this subpolar region, and it consists of a number of moorings, and also it is a gridded product, so they also assimilate data from Argo and gliders and things like that. And these observations have started in 2014, and they continue up to the present day. Hopefully they will continue to happen in the future as well. And what I wanted to show here, what I wanted to talk about, is the overturning in the subpolar North Atlantic and the metrics that we use to quantify the circulation. So in general, when people are doing some climate-related studies, when they are talking about the overturning, what they mean is that this is first of all, most people who are looking at climate models, for example, they're looking at overturning in depth space. So what does this metric capture is the circulation pattern, that is, we are basically integrating the meridional velocities from west to the eastern part of the basin, and also from top to bottom, or bottom to top, depending on how you want to do it. So in climate models, people mostly look at the overturning in depth space. And this metric characterizes the amount of lighter waters going in the upper layer to the north in the North Atlantic, and denser waters coming back in the south. And it does work really well in the subtropics, in mid-latitudes. But when we are in the subpolar latitudes, our isopignals, so the lines of the constant density, they're not parallel to the surface as they are in tropics, roughly. So it doesn't, and they are tilted, very much tilted. So it doesn't make a lot of sense to look at the overturning in depth space in the subpolar latitudes, because we have these lighter waters going in the north and denser waters coming back in the south, and it happens on roughly the same depth. So if you look at the overturning in the subpolar region in depth space, they just cancel each other, and you don't have a lot of insights from this metric. So another metric that is being used in the subpolar latitudes is the overturning in density space, when basically you do the same integration of these meridional velocities, but you don't, you basically have the not dz, but dz sigma. So it's you integrate it over the thickness of the certain density layer that you are interested in. So it's just like, because I will be talking about this metric a little bit later, so I thought it would be useful to give this quick introduction. So yeah, coming back to it, what I was saying is that biases in the density structure in the subpolar North Atlantic may lead to the overestimation of the strength of this circulation. And here, I just wanted to show you a plot from the paper by Tilles Petit et al. In 2023, when they basically compare, they use the Hadley Center climate model here in 3 different resolutions. So in low resolution, medium resolution, and high resolution. And they compare the overturning across this full OSNAP line, and also separately OSNAP West, so it's the Labrador Sea, and OSNAP East, so it's the Eastern Subpolar North Atlantic, to the model in different resolutions. And as you can see here, the observations are shown in black, and low resolution is blue, medium resolution is green, and high resolution is red. You can see that the model, especially in the high resolution, is overestimating overturning across the full OSNAP line in the Labrador Sea and also in the Eastern Subpolar North Atlantic. And the best performance among all of these models in 3 different resolutions is the low resolution model, even though it doesn't resolve a lot of things that we care about in this region. And this is kind of a paradox, because, I mean, it's not a paradox, it can be explained by the differences in the water mass transformations, and partly it can also be attributed to the differences in the density structures and how, in these models with different resolutions. Okay, and another thing that I wanted to say here, that if we are looking at, so this study is based on the global model, But if we are doing the regional modeling, some of these biases that we have in salinity and in density may also come from the open boundaries. And as modelers, you probably know that once you have some salt coming into the domain, it's really hard to get excessive salt. It's really hard to get rid of it. So it's really important what you set on the open boundaries in the regional, especially if you are running the regional model configurations. And here, just to illustrate this, I wanted to give you some example of this importance of density structure for the Subpolar overturning. So here is the upper panel shows the salinity, and also contours show density and the velocities from this observational OSNAP array that I was talking about. And the lower panel shows the salinity and also velocities from one of the previous model runs that I was doing with MITgcm. This is the regional configuration. This is the domain of my model. And I will talk a little bit later about its configuration. But what we can see here is that model that has been forced by the repeated year forcing for 2003-2004 in both the atmosphere and the ocean. At some point, it leads to the very large bias in the salinity. However, if we look at compared to the observations, however, if we look at the velocity structure, it's not dramatically different. So the exercise that I did here is I decided to see how, let's say we live in the perfect world when our model reproduces the density structure perfectly, whether it will help us to remove this overestimation in the overturning. So here, again, I'm showing the overturning in density space across the full OSNAP array, across the western part of the OSNAP and eastern part and the western part. So the black line here shows the overturning in observations, and the orange line shows overturning in the model in that configuration that I was talking about before. So we see straight away that the model overestimates overturning by quite a lot in both, especially in the west, but in the east as well. And here, the green line is the overturning that I computed using the velocities from my model and densities from the observations. So if my model would take the densities perfectly right. And we see here that when we do that, it helps us to reduce this bias in the overturning and kind of come closer to the observations, even though it's not like a perfect match, but it does help us a little bit. So yeah, density structure in the Subpolar region is really important. So yes, I wanted to kind of summarize the 3 points that I was making before. So we have these upcoming changes in the freshwater input in the Subpolar North Atlantic that may impact the ocean circulation there. We see that there is a very important role of the ocean density structure for the strength of the overturning circulation. And also that there is a salinity bias in general and high-resolution models, in particular in some of the regional models. So in this study, I want to investigate how the freshwater input via the East Greenland Current influences the overturning circulation in the North Atlantic. So I've done it with high-resolution regional configuration of MITgcm. Sorry about that, not CSM. So yeah, the spatial resolution was 1/12 of a degree, and this is my regional domain. So it was from 13 degrees south to approximately 70 degrees north with the sponge layers on open boundaries, which was also, this model was, ocean model was coupled with the sea ice model. And as a forcing, I've used GRA 55 DO for the repeated year, May 2003 to May 2004, which corresponds to neutral NAO. So we will not have any surprises from the atmospheric side, at least. And on the boundaries, on the open boundaries, I set the Arctic State Estimate, which is acronym for it is ASTI, which is basically a data constrained product based on ECHO. And in these experiments, I've used on the open boundaries the mean seasonal cycle of temperature and salinity averaged over 2011 to 2015. It has 50 vertical levels, and apart from the control run, which was forced with this repeated year forcing, I did 4 sensitivity experiments where I modified the salinity of the East Greenland Current, so the salinity of the waters that are coming into the domain from here, on the northern boundary of the domain. So yeah, this is what my sensitivity experiments look like. So basically, I applied anomalies to my salinity of, salinity on the open boundaries that would correspond to, here is the 3 sigmas, where sigma is interannual variability of salinity in this ASTI data for 13 years that this product is, has data for. In this region, in the East Greenland Current, from Greenland coast to 18 degrees west. And here, I've done it by making East Greenland Current fresher and making it saltier. But saltier is actually less fresh because East Greenland Current is fresh in general. So when I'm saying salty East Greenland Current, I mean just less fresh East Greenland Current. And I've done another 2 experiments when I just not to have like just 3 data points, but to have to observe the model response to even fresher or even salty East Greenland Current. So these 2 experiments, the anomaly corresponds to 6 sigmas. So it's like twice as large as in these experiments. Okay, so what effect does it have on the ocean circulation in the North Atlantic? And in particular, I will start with the impact on the ocean surface properties. So here, the upper line is the difference in salinity between my fresh AGC and fresher AGC experiments and the control. The middle line here is differences in temperature, and this is the differences in surface density. So we see here that when we make our East Greenland Current fresher, we see the fresh, and we see the fresh anomalies that are spreading along Greenland, and eventually, especially in the freshest experiments, we have this freshwater cap in the Labrador Sea, and this also is associated with the colder temperatures, and all of this leads to the lightening of these boundary currents in the Labrador Sea. Apart from that, we also see, so here the black line, I don't know, maybe it's not very well, not very evident from here, but yeah, the black line here is the position of the sea ice in winter in the control experiment, and the purple and blue line is the position in the fresh and fresher EGC experiment. So we see that we have some increase in the amount of sea ice in the Labrador Sea. So in the experiment, when we made this East Greenland Current less fresh, we see the spread of the salty and warm anomalies along the Greenland coast, which leads to the ice retreat, especially in the eastern part of the shelf in the Labrador Sea. And also another feature that we see here is that in the fresh and fresher East Greenland Current experiments, we have the stronger horizontal density gradient. Forget about it. Sorry, I mixed it up. So in the less fresh East Greenland Current experiments, we see the stronger horizontal density gradient in the region of the North Atlantic Current. So basically, this happens, and I will talk about it in the future, that it happens due to the northward shift of the North Atlantic Current, and we have the sharper salinity and density gradients here that acts as a barrier and reduces mixing with the subpolar waters, and this leads to the fresher interior of the subpolar gyre in the experiment when we have saltier East Greenland Current. So yeah, from changes in the surface densities, I wanted to make a step forward to look at the surface buoyancy fluxes. So here, the positive values of surface buoyancy fluxes mean that there is more densification of the surface waters, and the negative values mean that it's lightening of the surface waters. And here, when we have, again, fresher East Greenland Current, we see that there is a lightening of the surface waters that is happening in this region in the Labrador Sea. And we start noticing it in the first few years. So in the first year 2, 3, we already see these changes. However, if we run these sensitivity experiments for longer, so this one, for example, these are the differences that correspond to years 15 to 20, we also start, apart from seeing these anomalies in the Labrador Sea, we also start seeing the changes in the surface buoyancy fluxes also in the eastern subpolar North Atlantic. Another thing that I wanted to say is that in the fresh and fresher experiments, we see that these anomalies are in this region, while in the salty and saltier runs, these densifications primarily happen along the Greenland coast, so on the eastern shelf in the Labrador Sea. Yeah, I also wanted to briefly show the differences in the mixed layer depth. And we see, I mean, we would probably expect to see the decrease in the mixed layer depth in the fresh and fresher experiments, and we do see it here. But these negative anomalies are primarily attributed to basically the similar regions where we see these changes in the surface buoyancy fluxes. And in the salty and saltier East Greenland Current experiments is the same. We see the largest difference. We see the deepening of the mixed layer in the West Greenland Current here. Okay. So from the surface buoyancy fluxes, the next thing we look at is the surface water mass transformations, which is basically the surface buoyancy fluxes that has been, surface density fluxes that has been integrated for different surface densities. And what we see here is that there are larger surface water mass transformations in our less fresh East Greenland Current compared to the control and fresher East Greenland Current runs. And in particular, so this is the surface water mass transformations in this region in the Labrador Sea, so basically the western subpolar North Atlantic. And we see here that the changes in the, so the black is control, purple and blue is fresher experiments, and yellow and red is salty and saltier experiments. And what we see here, and this is different years here, 1 to 5, 6 to 10, 11 to 15, and 16 to 20. And basically what we see here that in the western subpolar region, the changes and the dashed line here shows the difference between the control experiment and the sensitivity tests. So we see that in the Labrador Sea, in the western subpolar North Atlantic, the changes in the surface water mass transformations appear almost immediately. So in the first years of anomaly, we already see the changes. And we also see that the freshening, so the purple and blue line, the freshening of the East Greenland Current leads to the larger impact than salinification, so that the orange and yellow line. And this is in the Labrador Sea. In the eastern subpolar North Atlantic, the region that is shown here, we basically see that the differences emerge later, so we don't see almost anything in the first 5 years. Then we start seeing something in years 6 to 10, and then this anomaly develops and increases. And this, here we see that the less fresh, so the saltier East Greenland Current has a minimal impact. So mostly we see the differences here that are coming from the freshening of the East Greenland Current. And then from the surface water mass transformation, the next step is to look at the overturning. So here I'm showing the overturning across the full OSNAP array that also is shown in the red line here. In the eastern subpolar North Atlantic and in the western subpolar North Atlantic. And basically in these 3 plots, what we see immediately is that I think that the differences are most evident in the western subpolar North Atlantic, so in the Labrador Sea. And we see here that when we add more fresh water to the East Greenland Current, it leads to the reduction in the magnitude of overturning and to the density, so like to lighter densities associated with the largest overturning. And when we increase the salinity, so when we make this current less fresh, it also increases in the opposite. It leads to the increase in the magnitude of overturning and densification, like the larger sigma associated with maximal overturning, but it doesn't change as much after a certain point. And we do see it as well in the full OSNAP overturning, that in case of freshening, we see this lightening and reduction in the magnitude in both of these experiments. And in the more salty and saltier East Greenland Current experiments, we see that it does increase to some level, but it doesn't move any further. And in the eastern subpolar North Atlantic, we also see this reduction in the magnitude of overturning, but we don't see a lot of the changes in the sigma of maximal overturning. And here between the salty and saltier run, we see mostly differences in the lower limb of AMOC. I also looked here briefly at the rapid line, so it's at 26 degrees north, and here is the overturning in depth space, and you basically also see the same effect. So reduction in the overturning strength for the fresher East Greenland Current experiments and increase in the overturning strength for the experiments with less fresh East Greenland Current. Okay, and as I said before, to kind of think about this overturning metrics, we are interested in both currents and also density structures. So here I'm showing the plot with the meridional, it's not meridional, it's the currents across the OSNAP line in the Subpolar North Atlantic in the control run, and then the differences between the fresh and control and fresher and control. So what we see in both of these fresher East Greenland Current experiments, that because we add more fresh water, this fresh current becomes even more fresh, and we have the stronger density, horizontal density gradient, which means that we have enhanced geostrophic currents in the upper 200 meters that we see in this that we see here. And also, because of this, these are lighter waters, we also have the increased stratification due to fresher, less dense upper layer. And we see the weaker deep currents here, the negative anomalies, and deeper currents here, I think because the vertical mixing is reduced. And we see the opposite picture in the less fresh East Greenland Current. So on the opposite, because the density gradient is lower, we see the weaker upper layer currents, we have lower stratification, more mixing between layers, and stronger currents below 200 meters due to the more energy transfer downwards. Okay, and the next part of it, so after the velocities, the next part is to look at the densities, because we kind of identified that the main things here seems to be happening in the Labrador Sea. So the next step is to look at the densities and also thermohaline properties of the Labrador Sea. So here I'm just showing two sections across the Labrador Sea in my control run. And generally what we have there is we have warmer and saltier waters that are entering the Labrador Sea via West Greenland Current. Then while they're going along the boundary current, these waters transform and they exit as colder and fresher Labrador Current. So in the fresher East Greenland Current experiments, as I've shown before, we have less surface transformations than in control run, and our waters enter and leave the Labrador Sea being fresher and colder. And the largest density difference, so the lower panel here is densities, and the larger density difference is observed in the upper 1500 meters. If we look at the less fresh East Greenland Current experiments, we see more transformation along the boundary currents, and we see the greater densification along the Greenland coast. And if we look at the differences in density, the larger differences here will be attributed to the lower layers. So the higher differences in density will be below 2000 meters in the Labrador Sea. So here I also wanted to show the adjustment of the sea surface height gradient and also the position of the North Atlantic Current, to talk about the intensity of the North Atlantic Current. So here I looked at the differences between the SSH, the sea surface height, on the exit from the Labrador Sea. So this panel shows the difference between the sea surface height on the boundary and in the interior of the Labrador Sea. And here we see that, so black is the control run, and we see that in both salty and saltier East Greenland Current experiments, we don't see so much difference between them. So there is some saturation after a certain point. It's not, we don't see much changes when we are increasing decreasing the amount of fresh water coming with this, with East Greenland Current into this region. And when we look at the fresh and fresher experiments, we see that it's more linear. So when we increase the amount of fresh water, this gradient is growing. It's a negative value, so it's it's larger. It's growing, and when we have even more fresh water with East Greenland Current, this gradient is even larger. And if we look at the region further downstream, so in the Gulf Stream separation region. Here I looked at the difference between sea surface height in 2 of these boxes. We also see that in the fresher East Greenland Current experiments, there is a lower SSH gradient than compared to the control run. And in the less fresher GC, there is not huge difference from the control run. Okay, and the last thing that I wanted to show here, that these changes in the strength of the North Atlantic current have implications for the heat transport. So this is the meridional heat transport across 50 degrees north. And we see that in the less fresh East Greenland current, we see the increase in the meridional heat transport. And in the fresher East Greenland current, we see the reduction. And yeah, again, in the salty East Greenland current, it's kind of reaches some saturation at some point. And in fresher, we see more linear effect. Yeah, the freshwater transport doesn't change yet, shows very high variability and very small mean differences. And this plot shows the differences in the surface currents. And as I told before, in the fresh and fresher East Greenland current experiments, we see the higher surface, the faster surface currents along the boundary, and in the saltier East Greenland current, we see that these current velocities are lower. But another thing that we see here is that when we have the less fresh East Greenland current, especially we see it in this experiment, we see that there is a northward shift of the North Atlantic current, especially in this experiment with the lowest freshwater influx. And this is somewhat similar to the results that Penny Holiday et al. Shown in 2020, when they also looked at the changes in the position of the North Atlantic current. But in their case, it was the wind stress curl that was driving the salinity anomalies in the Labrador current, and the more fresh water would come to the North Atlantic current, the more zonal it would be, the less fresh water would come to the North Atlantic current, it would be shifting to the north. In our case, we don't change the winds at all, but we just change the amount of fresh water that is coming into the domain. And yeah, basically we see that when we have less fresh water coming with the East Greenland current, it eventually leads to the, that it shifts to the north. Okay, to conclude this, I've shown hopefully that perturbing the amount of the fresh water coming to the Subpolar North Atlantic with the East Greenland current has almost immediate impact on the overturning in the subpolar latitudes. By almost immediate, I mean the effect that we can see in the first couple of years. When we have fresher East Greenland current, it leads to the lower magnitude of overturning with maximum attributed to the lighter densities. And on the opposite, when we have saltier or less fresh East Greenland current, it leads to the more intense overturning attributed to the larger densities. And this effect is most pronounced in the Labrador Sea. We also have shown that the response to the freshening is close to linear, while after the increase in salinity of the East Greenland current, after the certain threshold, it does not further impact the magnitude of overturning as much. And this is possibly due to the impact of freshwater influx on the surface transformations in the Labrador Sea and density in the upper ocean. And larger salinities leads to the larger transformations of the boundary currents in the Labrador Sea, and in particular over the West Greenland current. And also changes in the salinity of the East Greenland current, and I wanted to remind that it's just a forced ocean model, so it's not coupled with the atmosphere. It has implications for the position and the properties of the North Atlantic current and also meridional heat transport. And the larger influx of fresh water via East Greenland current leads to the more zonal position of the NAC, while lower influx of fresh water leads to the northward shift of the North Atlantic current. And that's everything. Thank you very much.
Questions for Rita? Justin?
I just had a quick question. It's a very nice talk. And the air-sea buoyancy flux, you said that was changed. What actually changes the air-sea buoyancy flux? Is it the surface temperature, or it's a forced ocean model, is that?
Yes, it is a forced ocean model. I think the changes, because the atmospheric part doesn't change, right? So this is changes. This changes due to the thermal component of the density flux. So it's probably due to the changes in the surface temperatures. So we have the difference between the air and sea temperatures is changing, and that's what leads to. I think that's how we explain it.
Next, Fred. Then Pete.
Nice talk, thanks, Margarita. So one of the first slides you show that essentially increasing the resolution tend to degrade the result. This is opposite of what we are finding in like a forced ocean simulation framework, like we are doing like this large intercomparison at OSNAP, and we have like 20-ish model with like low res, high res, and we consistently see that in the forced framework, moving to higher resolution get us more realistic OSNAP transport in density space. So the level were like HH, so I think those were based on like fully coupled simulation, right?
Yes, it is coupled simulations.
And so do you have a sense of like why you are seeing that? Because I was surprised.
Yeah, I don't know. I think it may depend on the model that you're using. So maybe it also have to do with this model being coupled. I mean, in some of the previous papers, they are saying that basically this density bias, salinity bias in the Subpolar North Atlantic is related to the larger transports of the more saline waters from the subtropics into the region. And once you have, because you have like more eddies and stuff, and then once you have it, it's like really, it basically stays there. But yeah, it's interesting. I haven't thought about it in the framework of like coupled versus forced models, and do you have? You don't have a center model in this comparison, right? It's a more
no. Well, we have many model, but not we have NEMO based model, and NOC is one of them, and in their model, when you move, we have 1 degree, quarter degree, and 1/12, and when you move to higher resolution, and again, it's not just one model, it's all the models show the same behavior in our comparison, but they are all like forced ocean model.
Yeah, maybe it has to do.
Yeah, I guess the mean bias is probably at play here.
We can take that one offline. Let's go to Peter.
This is great. So in the CMIP6 scenarios, we see the shutdown of AMOC and across all of the scenarios across the models. And even in overshoot scenarios, where we get warming and then we have cooling afterwards. And I'm wondering, you said there's this reservoir of fresh water in the Beaufort Sea. Is that sort of a precursor to the shutdown in AMOC, that you can't reverse it just by temperature? It's a freshwater driven thing, or am I just maybe oversimplifying what's happening here?
This is definitely one of the, because if you have a lot of the fresh water released in the North Atlantic, for whatever reason, if you're melting 3 Greenlands, like some people are doing in the papers or whatever, right?
Right.
So it doesn't really matter which source it would come from. It can be from the melting the entire Greenland. It can be from this fresh water release in the buffer gyre. I'm not sure. I'm not sure what's happening with the buffer gyre in the CMIP6 models, but I guess what's happening, I'm not deeply familiar with this kind of literature, but from what I'm understanding is that this, so we see the sea ice melting in the Arctic. This is all kind of accumulated in the buffer gyre. So, and it's like a paradox in a way that the sea ice is declining in the Arctic, but we don't capture it in the freshwater transports measurements in the North Atlantic, or just yet, so we don't see such large trends. So there is a concern that it may happen in the future. There are also some papers that are discussing that it depends on the phase of the Arctic oscillation, because obviously if this gyre is wind-driven, so if the wind patterns change, it may become weaker, and this water can start spreading in the North Atlantic. So I'm not quite sure what happens in the CMIP6 models and whether this is the impact of the buffer gyre freshwater release, or just generally the warming, the climate warming, the less of a difference between the less of a difference in temperature between the ocean and the atmosphere, and hence harder convection. And I'm not sure.
I was thinking about maybe the hysteresis of the fact that you go temperature up and you shut down AMOC, but you take the temperature back down, and you don't get the same acceleration back of AMOC. In the models, I don't know what the...
Yeah. Yeah, that's an interesting point for sure.
Dave?
So there's a bit of a conservation thing here. You talked a lot about the liquid freshwater part and the liquid freshwater flux, but what about the solid freshwater flux part of this? You know, because the thing is, maybe you're getting less sea ice and the freshwater staying in the ocean, but that also means there's less freshwater in the ice too. So you know, so I guess, have you investigated also changes in the solid freshwater flux coming through Fram Strait and through the Canadian archipelago?
Alice, then Bob, then who?
So kind of along those lines with the freshwater being stored in the Beaufort Gyre, like right now, there's a lot of ice in the Canadian archipelago, which prevents a lot of flow through there. And current CESM doesn't really capture any flow through there. Did your model, or do you have any understanding about like if freshwater came in both through the East Greenland Current, but also through the archipelago into the Labrador Sea, would that affect some of the results you have, or would it kind of lead to the same thing because you're still getting a bunch of
considered
pressure?
it, but maybe it would impact the results, because basically what I'm seeing here is let me think about, I'm just thinking like in terms of like what's downstream, right? Because when I see these changes in the eastern shelf of the Labrador Sea, of the whatever West Greenland Current, I guess if we have waters coming through Davis Strait, through Canada archipelago, it will be going kind of in the other direction, so the West Greenland Current will not be impacted. But the effect from the freshening of the East Greenland Current happened mostly kind of downstream from that. So I would say that probably, if we're thinking just about the increase in the amount of fresh water coming into the domain, I think that it may have some impact, but yeah, for the fresher case, I think it would be, that's a good question. I'm not sure which exact pathway it would take and like how it corresponds to the anomalies that I'm seeing, whether it's like upstream or downstream from that. I'm not sure. But yeah, it's a good point, because if it is released, it's here it's kind of like it's just part of the motivation. But yes, there are some papers that are showing that if the Beaufort Gyre collapses, whatever, the major pathway would be through Davis Strait, through Canada archipelago, and some of it will go through Fram Strait as well. So yeah, but we did consider it. Thank you.
So you run this at a 12th of a degree resolution, which is great, but there are still parts of your domain where you're not resolving the first baroclinic deformation radius, and clearly there are sub-mesoscale instabilities in the mixed layer that you're not resolving. Have you parameterized any of their effects? And if not, to what degree would you expect the results to change if you had been able to run at significantly higher resolution than you could?
That's a very good question, because I think it's one of the questions related to the amount of the freshwater release in the Subpolar North Atlantic, because obviously all of this is happening in the very narrow fresh boundary currents, and also there is some sub-mesoscale eddy exchange and things like that. So we didn't run it in higher resolution, unfortunately, but I think there would be some, I don't know, maybe more mixing of this fresh water in the East Greenland Current. Probably, but we didn't do it. We played a little bit with the sub-mesoscale eddy parameterizations in the MITgcm, but it didn't lead to huge change. But it may be, as far as I understand, this parameterization that exists now, it's not really well implemented, and this is it's tuned for. I think it's tuned more for the Labrador Sea, but not the East Greenland, not the Eastern Subpolar North Atlantic. I'm not sure. Anyways, we played with it a little bit, and we didn't see huge changes, but it may also have to do with how it is.
Just for clarification, that's the original Fox-Kemper et al. Scheme as opposed to Abigail Bodner's.
Yes, we played a little bit with the Fox-Kemper scheme.
State-dependent.
But it didn't. It didn't show huge changes there. But I don't know.
All right, well, last question from who, and I think there's no questions online, so who you get the last question?
Actually, I want to make a comment on Fred's question. So the MITgcm LL has wide sea ice coverage in the lab sea, so there's less water mass transformation going on. While if you go to higher resolution, the lab sea is open, so that's why you see more water mass transformation.
Yeah, it's. I wasn't advocating for for using low resolution models and abandon high resolution. Low resolution models are right for wrong reasons, but in some metrics, if you're looking through the lens of some metrics, they are more right than high resolution. But yeah, that's a really interesting point. I need to I need to think about it and kind of try to explain why it is. Yeah, it's interesting that in the forest ocean model is also improving with the increase in resolution.
Actually, I have a question. So you only consider freshwater anomaly along the East Greenland Current. So I assume that salinity anomaly comes with density compensating temperature anomaly. So when there's a freshwater, then cold. So have you considered that part of anomaly in your simulation?
I just changed the salinity that was coming into the open boundary, but when I show the differences for the surface properties, we see that in the experiments when we have cold anomalies, we also have fresh, no, that way around. When we have fresh anomalies, they are also cold, and when they are saltier, they're also warmer. But I mean, I didn't change it, I didn't change the temperature myself, but when we look at anomalies, we do see this cold, fresh, warm, salty thing.
Thanks. Yeah.
Okay, let's read it one more time. We'll be back at 1 p.m.